Concrete is one of the most common construction materials in use today. Before you can pour your concrete and build your structure, you need to determine if the concrete mixture is suitable for the particular application. Concrete consists of two phases: a mortar phase comprised of cement, water, and air, and an aggregate phase comprised of coarse and fine aggregates. When designing a concrete mixture, we need to ensure that the fresh concrete has an adequate rheology in order for it to be easily workable. The trial batch method is used to determine the characteristics of fresh concrete. This in situ test is meant to ensure that the concrete mixture at the batching plant has the same viscosity when it arrives at the construction site and is poured in forms. This video will discuss the main properties of concrete and illustrate how fresh concrete mixtures are tested in the laboratory. The trial method begins with samples of cement, water, coarse and fine aggregates, and target air content. The coarse and fine aggregates are assumed to be inert. The main variables we need to consider are the cement, water, and air. The water-to-cement ratio is very important because the strength of concrete is directly dependent on this quantity. Concrete strength is customarily measured at 28 days after casting, and typically varies in terms of water-to-cement ratio from about 0.35 for high-strength concrete to about 0.6 for low-strength concrete. A lower water-to-cement ratio decreases the permeability of concrete by reducing the penetration rates of salt ions into concrete and thus the corrosion of the concrete reinforcement. High curing temperature and humidity significantly accelerate the strength gains. The air content of a fresh concrete mixture plays an important role in durability, especially for concrete used in regions that undergo cycles of freezing and thawing. Free water expands as it freezes and turns to ice and can crack the concrete. The air bubbles in the mix allow this expansion without cracking the concrete. A higher amount of air results in a lower strength, so for a given strength, a higher water-to-cement ratio is necessary. Strength and durability are long-term properties of concrete. The short-term properties, such as workability, need to be taken into account as well. In the next step of the trial method, coarse and fine aggregates are added to the mixture to achieve the desired plastic consistency. The amount of coarse aggregate and sand will be adjusted during batching to achieve adequate workability and slump for the concrete mix. The slump, or concrete's flowability, measures the consistency before the concrete sets. The slump test consists of pouring and compacting fresh concrete into an inverted cone in 3 layers. Once the cone is filled, the cone is lifted and the amount that the concrete slumps or subsides is measured. Results of the slump test are an indication of the cohesiveness of the mix. A well-proportioned mix will fall but retain its original shape. A poor mix will crumble, segregate, and fall apart. Now, let's look at the concrete mixing practices in a laboratory environment and learn how the trial batch method is used to prepare concrete test cylinders for subsequent applications. Weigh out and separately store the given quantities of coarse aggregates, fine aggregates, cement, and water. Record the exact weights on the datasheet. Before you begin mixing, dampen the inside of the mixer and all of the tools so that they are wet without leaving any standing water. Now put the coarse and fine aggregates into the mixture with about 1/5 of the water. Allow these components to mix for about 2 minutes. With the mixer still rotating, add the cement and additional water in 5 to 10 small increments. When you have finished adding these components, let them mix for another 5 minutes and then turn the mixer off. You are now ready to test the slump of the concrete mix. Dampen the slump cone and place it in the mixing pan with the large diameter down. Hold the slump cone down firmly against the pan, and then fill about 1/3 of the volume with a layer of concrete. Tamp the layer with 25 strokes distributed uniformly over the cross-section of the cone. When you are finished, add 2 more layers of concrete, tamping each layer so that the rod penetrates slightly into the previous layer. Strike off the excess concrete so that the cone is completely filled but not overflowing. Immediately lift the cone carefully and vertically to separate it from the concrete. Then determine the slump by measuring the difference between the height of the mold and the height of the concrete. The slump of this mixture should be between 3 and 4 inches. If it is too low, or the mix appears harsh and does not flow properly, gradually add small measured quantities of fine or coarse aggregate as appropriate. Then thoroughly remix and retest the concrete until the desired slump and consistency are achieved. Now that the mixture is correct, weigh the remaining aggregates and record these values in the datasheet. Compute the actual amount of coarse and fine aggregates used in the concrete mix from the initial weights. Finally, determine the unit weight of this concrete mix. Record the weight of an empty 1 cubic foot container, and then fill the container with concrete following the same procedure used to fill the slump cone. Weigh the full container and calculate the unit weight for this mix by subtracting the empty container weight. Prepare 4 cylindrical molds for casting the test samples. Measure and record the empty weight of each mold on the datasheet. Fill each mold by following the same procedure used to fill the slump cone in the previous section. After filling each mold, measure and record the filled weight on the datasheet. Cover the molded concrete with a plastic bag to prevent evaporation of water from the mixture. Leave the test cylinders to set for 16 to 32 hours, and then strip the disposable plastic molds from the concrete specimens. Finally, place the cylinders in the curing environment. In this case, the cylinders are left to cure in ambient conditions. Now that you understand how to determine the characteristics of fresh concrete, let's review the results. The quantities and materials used in this experiment to prepare the concrete mixture are shown in this table. Our fresh concrete mix had a slump of 3.5 inches. In general, mixes such as the one described in this experiment have slumps of 3 to 4 inches. Such values are common for small jobs with little steel congestion in the forms. The unit weight of our concrete was 147 pounds per cubic foot. The unit weight of normal weight concretes is around 145 to 150 pounds per cubic foot. But concrete made with lightweight aggregates, expanded shales for example, may be as light as 100 to 120 pounds per cubic foot. The water-to-cement ratio for our concrete batch is 0.45. This ratio indicates that the compressive strength of our test cylinders at 28 days will be around 5,000 psi. This ratio also indicates that the durability of our concrete makes it suitable to exposure to freezing and thawing in moist conditions or de-icers. The trial batch method is used on many construction sites around the world to test batches of concrete. This simple test ensures consistent quality control and assurance at the worksite. Superplasticizers are chemical additives that considerably reduce the viscosity of a fresh concrete mix for a short period of time, in order to allow for ease of placement into the forms. In modern construction, the widespread use of superplasticizers has meant that it is economical to get much higher slumps in the 6 to 10 inch range, corresponding to self-leveling concrete. Air entrainment agents are chemicals that create many small, well-dispersed air bubbles and provide the spaces necessary for free water inside the concrete mixture to expand during freezing without cracking the concrete. Air entrainment testing of fresh concrete is device-specific. For example, pressure is applied to the sample to compress the entrained air in the pores. The device uses the change in air volume to determine the air content of the mix. Non-air entrained mixes will show air contents below 2%, while air-entrained mixes, depending on the additive's dosage, will show 5 to 8% air content. You've just watched Jove's introduction to tests on fresh concrete. You should now understand how the trial batch method is used to determine the optimal proportions of aggregates, cements, and water to prepare concrete that meets slump requirements. Thanks for watching.